Okay, so we've talked about Taylor series, and I mentioned at the end of the last video that we're going to move on and we're going to start talking about instead what are called Taylor polynomials. And, Maclaurin polynomials, whatever. Of course, just like the series, Maclaurin one is one that is centered at 0, so an a value of 0. So this would be the representation of the Taylor series for f of x. The whole thing is that sometimes we don't want the series because we don't really need all that specificity. Sometimes the first few terms is enough. So if I have the first few terms right here, and then I cut it off, right? Just boom, cut it off. That is what is known as a Taylor polynomial, right? And we don't use f of x, we use p sub n of x, or some related style of thing. And basically that says, and the n, of course, is how many terms it's gone out to. So if you're looking for the fifth degree Taylor polynomial of something, it would be p sub 5 of x, okay? Now, obviously, there is a difference between f of x and p sub n of x, okay? Basically, all the rest of the terms, right? And all the rest of the terms, and each term becomes, more and more insignificant in terms of affecting the actual values that are spit out. But at some point, you kind of truncate because the value's good enough, okay? You don't really care about, the 101st term of it, because the first 100 terms give you, an approximation that's, correct to 52 decimal places or something like that. And this is actually what your calculator uses. Your calculator uses a Taylor polynomial for sine x to give you your values for sine correct to, however many decimal places, 8 or 9, or however many our calculators are programmed for. And they have a way of figuring that out. Because basically, f of x minus p sub n of x, if you take the difference between there, obviously this would be equal to that if it had the remainder of the term. So the difference between these is what we refer to as r sub n of x. And r sub n of x is just basically just notation that says this, okay, is basically stands in for all the rest of those terms that are missing once you truncate the series into a polynomial. It's really that simple. And you think to yourself, how in the world would I figure out how good my approximation is? And it just so happens that there was this mathematician named Lagrange, and of course every time I say his name or see it written, I think of the ZZ Top song. If you don't know what I'm talking about, you're an uncultured Philistine, and I feel sorry for you. But basically, your r sub n of x, it basically, if you get to the nth term, right? The nth term of any Taylor polynomial or any Taylor series would be the nth derivative at a over n factorial x minus a to the n. That is the nth term, correct? Okay, so if that's the nth term, r sub n of x is related but not the same as the n plus 1th term, okay? So we have the n plus 1th derivative over n factorial, or n plus 1 factorial x minus a to the n plus 1. The difference is I'm not going to put a right there because I don't necessarily want a. I want some number c, or some books actually put z right there. I want whatever value is going to maximize the n plus 1th derivative. And once I've maximized the n plus 1th derivative, that's the value that I put here in the numerator. And because it's a sort of maximized value, some some books don't even put this up here. They just call it m, and they basically says, and basically the m is the maximized value of that n plus 1th. It's kind of hard to say, derivative. And you're wondering, well, what does that mean? Okay, well, I'm going to go ahead and show you what that means. Let's say that we are asked to find the 5th degree Maclaurin, sorry, that C kind of melded with that D and made it look like Madurin, but Maclaurin polynomial for y is equal to sine x, okay? And Maclaurin meaning that it's centered at 0, okay? And so basically what we're looking for is we're looking for a truncated version of this, which we already know. So we're looking basically for that. And then we're going to ask ourselves a question as to how well that actually approximates a particular value of sine. Now, the approximation is obviously going to be better for a value that is closer to the point of centering, okay? So if I basically say my p sub 5 of x is equal to those first terms up to the 5th degree, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and of course that is my approximation of sine x. That is centered at 0. If I ask you for an approximation of, sine of 0.1, that's going to be a better approximation than sine of 0.2, because sine of 0.1 is closer to the point of centering. As you go away, since this is an approximation and not actually convergent with the function at all points, it's going to be worse and worse approximation the further and further you get away from the centering. I want to know, for our purposes right here, how well does it approximate sine of 1? And by 1, I mean not 1 degree, but 1 radian, okay? Okay, well, let's go ahead and actually plug that in and see what happens. Okay, we can actually, since we have our calculator right here, we can actually do sine of 1, okay, and then we can 1 over 3 factorial plus 1 over 5 factorial. Okay, and that winds up being, our difference, right? So I want to put that there, and then minus that, and let's see what the difference is. Okay, well that's a pretty good approximation. But let's say I didn't have my calculator in front of me, and I simply needed to maximize it. I simply needed to find out how good of an approximation it was. I'm not going to get this difference right here, but what I am going to get is I am looking for how big can the error possibly be? What is the maximum that the error can be? Knowing what I know of this function and knowing what I know of the Maclaurin series and therefore the Maclaurin polynomial that is here to approximate it. Well, like I've told you before, if I'm looking for r sub 5 of x, that is going to be the 6th derivative of sine. Now remember, if I have y is equal to sine x, then y prime is equal to cosine x, y double prime is equal to negative sine x, y triple prime is equal to negative cosine x, and the 4th derivative, or I should have put that in, the little 4 in parentheses up there, goes back to sine x. So the 5th derivative is cosine x, and the 6th derivative is negative sine x. So I'm looking for negative sine of c. I'm looking for the maximum value of negative sine. Now, I also know that I'm going to put 6 factorial down here, and I'm going to put 1 to the 6th out here, right? Because this is the specific form of this, which is f to the n plus 1th derivative at c over n plus 1 factorial and x minus a to the n plus 1, right? Now, obviously, my a is 0. I'm plugging in 1, that's my x is 1. So 1 minus 0 is 1. Obviously, if this is the 5th, I'm looking for the 6th, the n plus 1, that's 6 factorial. The curious part that may seem a little uncomfortable for us is that here's the great thing about when you're asked a question like this for sine and cosine. You don't have to finagle with anything. You know that sine and cosine oscillate between -1 and 1. So the maximum value for sine, negative sine, cosine, or negative cosine is just 1, okay? So basically you just kind of put a 1 in there and you just go from there. Now, that means that my r sub 5 of x, my maximum error that could possibly be the case, 1 to the 6th is 1, that numerator is 1, is 1 over 6 factorial. Okay, and therefore what I have here is if I go 6 factorial, okay, I'm going to get 720, right? That should be a familiar number to us. And so what happens when I reciprocalize that? I get 0.00138. Okay, so that's 1 over 720, which is approximately 0.00138. Okay, 889. That is the maximum error that sine of 1 can have from what it actually is. And all you do is just take the next term, but instead of actually evaluating that numerator, you actually just maximize what that n plus 1th derivative can be. Now, this is for a sine and cosine one, so that's a little bit easy because you just go, well, it's sine and cosine. I'm using Lagrange error for sine and cosine. It's just 1, okay? Let's actually look at another example, and let's do an example dealing with the function e. Okay, I think that would actually be instructive. Let me go ahead and get another problem out right here. Let's say that I am looking for the 4th degree Maclaurin polynomial for f of x is equal to e to the x. And what I want to do is let's actually try and use that to find out what the error is for y, for e to the, oh, I don't know, let's do e to the 1/2. Okay. So, I know that it's a Maclaurin polynomial, which means it's centered at 0. I'm going to be plugging in 1/2 to find out what the approximation is, and then of course not only what the approximation is, but what the error possible is for that approximation. So really I'm dealing with the interval 0 to 1/2. So I know that my e to the x, my 4th degree polynomial for e to the x, is basically the first up to here to x to the 4th. Okay, so it's actually going to be 5 terms because we start with the 0 degree term. Okay, so I know that my polynomial to the 4th degree is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. And if you want to get rid of the factorials, you can just do, x squared over 2 plus x cubed over 6 plus x to the 4th over 24, if that helps you out. Now I happen to know that my r to the 4th of x is going to be the 4th, or if this is the 4th run right here, it's going to be the 5th derivative. Well, the great thing about e to the x is the 5th derivative is the same as the 1st, 2nd, 3rd, and 4th. It's just e to the x. So I'm looking for e as e to the c that's maximized on this interval from the centering to what I'm actually approximating at. I also have, this was 2 factorial, 3 factorial, 4 factorial. This needs to be 5 factorial. And then I need to go ahead and plug in 1/2 to the 5th. Well, where is e to the x maximized on that interval? Well, it's maximized since you happen to know what e to the x looks like. E to the x is a monotonic function. It's increasing. So from 0 to 1/2, if this is 1/2, the maximum is obviously at 1/2, right? And it's e to the 1/2. So what I need here is I need e to the 1/2 over 5 factorial over and times 2 to the 5th. And all I've done is simplify this into 1 to the 5th over 2 to the 5th and shove that 2 to the 5th down here in the denominator. Now, let's go ahead and reason how good or bad that approximation is. Let's go ahead and get ourselves a ratio in here, and we'll do the square root of e, 5 in math probability 4, times 2 to the 5th, and that's probably going to be rather large since 5 factorial is 120 and 2 to the 5th is 32. And look at that. That is an extremely small error, okay? So basically what that's saying is that the maximum error that you can possibly have for e to the 1/2 being approximated by this 4th degree polynomial is, and e to the 4th is obviously 10 to the negative 4th, so just basically move the decimal place back 4 places, and basically it's 1, 2, 3, okay, 4, 2, 9, 3, 5, 4, 4, 9, 7. That is the maximum error. Well, that's pretty tiny, because that's the 10th spot, hundredths, thousandths. That's a little more than 4 10,000ths in terms of error. Okay, so that's what's called Lagrange error. Lagrange error is simply a matter of taking the n plus 1th term and tweaking it just a smidge and not actually evaluating the numerator, the n plus 1th derivative at a, but maximizing that n plus 1th derivative on the interval, which is the centering to whatever value that you're actually approximating. And here's the thing. Let's say that I instead wanted to approximate e squared, right? Well, it would still be the same sort of thing, except for I would get, r to the 4th, and it would be e to the c would be e squared because, just like this original one, and it would be over 5 factorial, and it would be 2 to the 5th. Well, that 2 to the 5th is now hopping up here in the numerator, right? And that's going to be e squared times 2 to the 5th over 5 factorial. That's going to be a completely different error, and it's going to be a much larger error because 2, it's now an interval not from 0 to 1/2, but it's an interval 0 to 2, and I've already told you that the farther you get away from the centering, the greater the error is going to be, okay? And they can ask the question about error in a very straightforward fashion like this, or they can basically do it in reverse, and they can say, how many terms must I have for my Taylor or Maclaurin polynomial in order for the error to be less than, 0.001 or something like that. And that would be the same. That would be sort of the same idea. Or they could basically say, okay, how about can e squared be equal to a certain number? Okay. And basically, based upon what the actual value is, and the maximum error would go both ways. And you could say, yeah, that actually could be a value for it, or you could say, no, that isn't. That's outside of the error range. So there are several different ways that you can actually get at this, but this is the basics of what's called Lagrange error. Now, here's the thing. Remember that error is not specific to these types of problems. If you have an alternating series, error is not done by Lagrange. Error is simply, the maximum error is simply the very next term. Okay, and you'll see examples like that as well. We're coming up on about 20 minutes, so we'll go ahead and sign off on this one. If you have any questions, as always, please do email me. Bye.